Okay, today we will talk about a very important topic that's also quite interesting. I think it's actually kind of cool. Linear programming duality. Every linear programming problem has what's called a dual problem, which is a very similar problem with the same numbers, but asked in a slightly different way. So let me give you a immediate example. Take the problem we were working on with the popcorn and soda and the two different kinds of snack packs, right? So that's on the left here, and you could say that this problem is posed from the customer's point of view. How do you buy enough popcorn and soda at a minimum cost, right? That's the kind of a problem a customer might have. So, okay, I'm just reminding you how we set it up earlier here, right? I worked out the solution. By the way, this solution isn't realistic because it requires you to buy 1.2 of the first snack pack and 4.2 of the second snack pack. I don't think most movie concession stands will let you buy a fraction of a snack pack. But theoretically it makes sense, right? If you could do that, this would be the optimal way to do it. And it would cost $39.16. By the way, it's worth pointing out that there are varieties of linear programming problems where you restrict the values that the solution can take to whole numbers, right? So you can do that too, but I'm not going to talk about that because I think we've got enough to be going on with by talking about solutions with real numbers. But that is a thing, and you can do that as well, right? Okay, now you can also look at the same situation with the two snack packs and the popcorn and soda, but you can look at it from the point of view of a business that's trying to sell popcorn and soda. And we can ask the question, gee, what prices could this business sell popcorn and soda at, right? So I'm going to use YP for the price of the popcorn and YS for the price of the soda. And we could ask, what prices could they set for popcorn and soda in order to, well, clearly one thing they're going to want to do is they're going to want to maximize profit, right? So they want to maximize their profit. That's what a business wants to do. So we want to maximize, and by the way, we know that you're a customer who wants to buy 44 ounces of popcorn and 56 ounces of soda. So they want to set the prices so that they maximize this quantity, right? That basically the dot product of 44.56 with Y, right? So 44 ounces times the price of popcorn plus 56 ounces times the price of soda. And that's the quantity they'd like to maximize as far as getting the most money out of you, right? On the other hand, they have to remain competitive with the prices that the concession stand is offering, right? In other words, if you work out what the price of 12 ounces of popcorn plus 8 ounces of soda would be, right? So 12 YP plus 8 YS, that would be the price of the same amount of soda and popcorn that is provided in the first snack pack. So in order for you to remain competitive with the concession stand, you have to charge no more than $8 for that combination of popcorn and soda, right? If you charge more, then there's no reason for them to buy from you. They're just going to buy from the concession stand. And similarly, you also have to keep your prices in line with the other snack pack. So seven ounces of popcorn times the price that you want to charge for popcorn plus 11 ounces of soda times the price you want to charge for soda. That has to remain less than or equal to the $7 that the concession stand charges for the same snack pack, right? For the equivalent snack pack. So you're restricted, in order to remain competitive, you're restricted or you're constrained by these inequalities, right? Now, interesting thing. If you solve them, you find that, of course, you work at whatever Y is. So it turns out that you should charge, what is this going to, it's going to be 0.42 42 cents per ounce of popcorn and about 37 cents per ounce of soda. And if you do that, you will make a profit of $39.16. And the thing to note is that the maximum profit that the business can make is exactly equal to the minimum cost that the customer had to spend in the other problem. Okay, now these two problems, the one from the customer's point of view and the one from the business's point of view, they're called dual problems. They both use exactly the same numbers. And notice the relationship of the numbers. In the first problem, the 8 and 7 were in the objective vector. In the second problem, the 8 and 7 were in the constants on the right side of the constraints. And similarly, in the original problem, the 44 and the 56 were the constants that formed the right side of the constraints. But in the dual problem, they form the objective vector, right? So what happens is the relationship between the original and the dual problem, the objective vector and the constraints, the vectors B and C, change places, right? They exchange places. On the other hand, we had this matrix A over here, which represented basically how much popcorn and soda was in each of the two snack packs, right? There were 12 ounces of popcorn, 8 ounces of soda in the first snack pack, and 7 ounces of popcorn, 11 ounces of soda in the second snack pack. The matrix A is used in the dual problem, but it's transposed, right? So we just transpose the matrix, turn the rows into columns, and that's the form that we have over here, right? So the two other important differences. The original problem was a minimization problem, whereas the dual problem was a maximization problem. And finally, in the original problem, the constraints were greater than or equal to. A times x had to be greater than or equal to this constant, whereas in the dual problem, the constraints were less than or equal to, right? The A transpose times y had to be less than or equal to this vector, right? So, however, it's a very mechanical difference, right? Everything is slightly tweaked, everything is slightly turned around, but it's a very mechanical procedure. You can always manufacture a dual problem starting from any given linear programming problem, right? And by the way, depending on what's convenient, we may refer to them. In this case, I've been calling the maximization problem the dual of the minimization problem, but I could do it the other way. I could say that the minimization problem is the dual of the maximization problem, right? Each one is the dual of the other. Okay, so now let me just state the duality theorem formally and as concisely as possible, right? So in general, if you have one problem, which is a minimization problem, it's of the form minimize b dot x subject to the constraints that x is greater than or equal to 0 and ax is greater than or equal to c. And the dual problem is a maximization problem where you want to maximize c dot y subject to the constraints that y is greater than or equal to 0 and A transpose y is less than or equal to b, right? So these problems are dual to one another. Then the conclusion of the theorem is that both problems have the same optimum value. In other words, the minimum of the problem on the left is always equal to the maximum of the problem on the right. Now, it's actually quite easy to show that the maximum on the right, c dot y, is always less than or equal to the minimum of the problem on the left, right? So what you can say is that if you're multiplying c dot y, so that's the objective function for the maximization problem, well, in matrix terms, that's just equal to the matrix product of c transpose multiplied by y, right? You take the column vector c, turn it into a row vector, and then you matrix multiply them together, and that's equivalent to taking the dot product. Now, recall that in the first problem, one of the constraints was that 8x is greater than or equal to c. If I just transpose everything here, then I get this, then A times X transpose becomes X transpose times A transpose. And that, as we saw, is greater than or equal to C, or C transpose, right? So what I've done here is I've used the fact that C transpose is less than or equal to X transpose times A transpose, right? Now, you might worry about applying this in the case of a matrix equation, but in fact, everything in y is non-negative, right? That's one of the constraints on y. It's non-negative. So it's perfectly okay to apply this inequality even in a matrix equation. We don't have any negative numbers that we have to worry about reversing the direction of the inequality or anything like that. So okay, so as long as AX is greater than or equal to C, we know that X transpose A transpose is greater than or equal to C transpose, and so this inequality is valid. Now if you just regroup over here, just rewrite this X transpose times A transpose times Y as X transpose times the quantity A transpose times Y, then we can use this other inequality over here. So this says that A transpose times Y is less than or equal to B, and now I'm going to do the same thing. I'm going to say since this is less than or equal to B, then we get this inequality. And again, we're appealing to the fact that X is a vector of non-negative numbers. That's one of the constraints on X. And therefore, this is a perfectly valid inference to draw, right? As long as A transpose is less than or equal to B, then, A transpose Y is less than or equal to B, then X transpose times A transpose Y will be less than or equal to X transpose times B, right? And then finally, X transpose times B, that is just B dot X, right? Again, we're just transposing the X vector and make it a row vector, and you multiply it by the column vector B. That's the same thing as the dot product B dot X. So this verifies that any solution, even if it's not optimal, even if it's not maximal, any solution to the second problem is always less than or equal to any solution, even if it's not optimal, to the second to the first problem, right? So any feasible solution, meaning it satisfies the constraints, but it may not be optimal. Any feasible solution to the max problem is no greater than any feasible solution to the min problem, right? This is good to know. This means, together with the duality theorem, this tells us that there's going to be, exactly one case of an overlap, right? So the maximum to the second problem will always be exactly equal to the minimum of the first problem, and that is the one and only place where the two objective values can overlap, right? Only at the maximum of the second problem can be equal to the minimum of the second problem, but no other feasible solutions will be equal. Another way to put it is that if you ever come up with a pair of solutions, or a feasible solution to both problems, right? So X is a feasible solution to the first problem, and Y is a feasible solution to the second problem. If you happen to find that they both produce the same objective value, there's no way that could happen unless the solution to the second one is the maximum and the solution to the first one is the minimum. So in other words, if you ever find that's the case, you will have solved both problems, right? The only way to get the optimal values to overlap is if you have a solution to both of them, right? Otherwise, they will satisfy this inequality, but they won't be equal. Okay, now I'd like to address the question of why the two solutions should be equal, right? Why should the solutions to these dual problems actually be equal? I'm not going to give a formal proof, but I will give another example that I'll do in detail, and I think this will kind of explain intuitively why it is that the two solutions, the solution to the maximum problem and the solution to the minimum problem, always have the same value for the objective function. Okay, so this problem is very similar to the popcorn and soda problem. It's just slightly more complicated. But basically, instead of having two things that we want to consume, right, and the other problem was just popcorn and soda, here there are three things. And however, there are still two different packages you can buy them in. Okay, but this problem is in the form of a vitamin problem, a health problem. Let's say that your doctor advises you that you need to take some vitamins to keep your vitamin P, Q, and R levels up, right? You're showing a dangerous deficiency in vitamins P, Q, and R. So he tells you should get at least 100 milligrams of vitamin P every day, 80 milligrams of vitamin Q, and 110 milligrams of vitamin R. Okay? Now, the store sells two different brands of vitamins that provide P, Q, and R. And one brand contains 20 milligrams of vitamin P, 5 milligrams of vitamin Q, this is per pill, and 15 milligrams of vitamin R per tablet. And each tablet costs 70 cents. There's another brand at the drugstore where each pill or tablet contains 10 milligrams of vitamin P, 10 milligrams of vitamin Q, and 10 milligrams of vitamin R. And that one costs 60 cents per tablet. Your problem is how many pills of each brand should you take in order to get your necessary vitamin requirements as specified by your doctor, but at a minimum cost. Right? You want to pay as little as possible for the vitamins that you're taking. Now, in this case, you can cut up pills, so it is perfectly reasonable if we get a fractional answer here. We can just take a fraction of a pill, right? In fact, they actually sell like pill cutters you can use to cut pills up into pieces. So that's definitely a thing. Okay, so now our unknown vector x is, it's a column vector where the first entry is how many tablets of the first brand we will take, and the second entry is how many tablets of the second brand we will take. And then the objective vector b consists of the prices of the two tablets, right? So the first brand is 70 cents per tablet, the second brand is 60 cents per tablet. So our goal here is to minimize the dot product b dot x, right? The price times the quantity of each tablet. C represents the minimum requirements you have for each vitamin, right? We need 100 milligrams of vitamin P, 80 milligrams of vitamin Q, 110 milligrams of vitamin R. And the A matrix is kind of like the ingredient matrix or the recipe matrix, right? So the first column tells you what's contained inside the first brand of tablets. It contains 20 milligrams of P, 5 milligrams of Q, and 15 milligrams of R. The second tablet contains 10 of each. And so when you multiply A times X, right, where X contains the number of tablets of each brand that you take, what you get is your total vitamin consumption from the tablets, right? And that has to be at least as great as C. So that's this constraint here. And of course, we can't take a negative number of tablets, so X has to be a non-negative vector. Now you can easily plug this one into Mathematica and find the solution. So I did that, and we found that the solution is you should take 3 tablets of the first brand and 6.5 tablets of the second brand, and then you will get your dietary requirements satisfied, and it will only cost $6. And that's actually the minimum cost if you want to get these dietary requirements from these 2 tablets. Right? Okay, so here's a surprise. It turns out that the dual problem is exactly equivalent to the problem of calculating the shadow prices. So let's just look at this carefully, right? And I'll convince you that that's the case. The dual problem would be when you maximize C dot Y, subject to y is greater than or equal to 0, and subject to A transpose y is less than or equal to B, right? So we've exchanged the places of B and C. We replaced minimize with maximize, we replaced A with A transpose, and we changed the direction of this inequality, right? So this is the dual problem. Now, if you think about what this is saying, it's saying let's find a vector y. Let's say y consists of 3 variables, p, q, and r, such that multiplying or dotting y times c, and recall that c was the vector of vitamin requirements, right? So how much of vitamin P you needed times the price of vitamin P plus how much of vitamin Q you needed times the price of vitamin Q times how much of vitamin R you needed times the price of vitamin R. That gives you the total cost, right? And from the point of view of the shadow prices, Now we want to look at this problem from the point of view of a business, right? How do we maximize our profit? What prices should we set in order to maximize the profit that we can make from this customer, right? Customer has to buy quantities given by the vector C of each vitamin, and the prices are given by Y. So C dot Y gives us the total profit that we will make, or at least the total income we will get from this customer, which we want to maximize. It's subject to, of course, Y has to be non-negative, right? We're not going to set our prices to be any negative numbers. And then this third or line, or the second constraint, A transpose Y is less than or equal to B. Here I've written it out in more detail so you can see it a little better. A transpose is this, and when we multiply A transpose times the prices, or shadow prices PQR, what we're picking up again is the first row represents the cost of the first pill, right, or the cost of vitamins equivalent to the first pill, right? The cost of the vitamins in the same amounts as in the first brand, right? And that total price should be less than or equal to 70 cents in order to remain competitive with the tablets, right? Again, if you're looking at this from the point of view of a business, you want to charge high prices, but you have to remain competitive with the existing products on the market, right? So in order to remain competitive, it has to be the equivalent in vitamins would have to be less than or equal to whatever the price they're charging for the tablets, right? And similarly, the equivalent in the vitamins for the second tablet has to be less than or equal to 60 cents. Okay, so if you solve this dual problem, you're basically solving the shadow prices problem from the point of view of a businessman who wants to maximize profit, right? Now, we already have our solution, right? We worked out the solution earlier. We got the solution P equals 0, Q equals 2, R equals 4. Now, does this satisfy all the constraints? Well, yes, it's non-negative. In fact, we have equality here, right? Because when P is 0, it just reduces to 5Q plus 15R equals 70. Remember, that was the equation that we solved over here, right? So in fact, we solved this system of equations in Q and R. So we know that, in fact, we're going to have equality here. So in particular, this inequality is satisfied. And furthermore, it's because it gives the same objective value that we got in the original minimization problem, we know that this must also be the solution to the maximization problem, right? Because of this inequality, let me go back here, because of this inequality we saw earlier, the solution to the maximization problem is always less than or equal to the solution to the minimization problem. If they're ever equal, which they are in this case, right? We saw that we got the same answer for the price using the shadow prices, right? For the cost of the vitamins using the shadow prices, it produces the same cost as we got under the minimization problem. So since this solution provides the same value for the objective function that we got in our original minimization problem, this must actually be the maximum value of the in the dual problem, in the maximization problem, right? So in fact, the solution we worked out for the shadow prices is in fact the optimal solution for the dual problem. And so in this case, at least in this case, we see that starting with the minimization problem, we were able to work out the shadow prices, and the shadow prices were a solution to the dual problem. And so both problems have the same solution in the sense of the same value for the objective function, right? Now, this isn't a proof that this is always the case, but trust me, it is. In fact, it can be shown in general that the solution to one problem always leads to a kind of equivalent solution to the dual problem. There's one other feature of the particular problem we look at, the vitamin problem, that does generalize to all linear programming problems and the relationship between the original problem and its dual. Recall that in the example we looked at, we found that there was one constraint that was slack, right? That the constraint on vitamin P was slack, and we interpreted that as meaning that the shadow price of vitamin P would be 0. Now this actually generalizes perfectly, right? So the way to generalize it is that you say if in one problem one of the constraints is slack, right, that the constraint actually is a strict inequality, the two sides are not equal, then, and only then, the corresponding variable in the dual problem will be 0 in the optimal solution. Right? So, this concept is called complementary slackness. It says that a constraint is slack in one problem if and only if the corresponding variable is 0 in the solution to the dual problem. Right? And vice versa. I mean, I said if and only if, right? But it means that if you have a variable equal to 0 in one problem, then the corresponding constraint will be slack in the other problem. And this is quite useful because what it tells you is that if you notice, if you got a constraint which is slack, that means you don't even have to worry about one of the variables in the dual problem. You know it's going to be equal to 0, so you can just eliminate it from the problem. So complementary slackness, this is a tool for simplifying the dual problem, right? If you solve one problem, maybe if you very often you may have to solve both problems because you might want to know what the optimal solution to the minimization problem is, but you might also want to know what the shadow prices are, right? You might want to solve both. Complementary slackness suggests that what you do is you solve the simpler one first, whichever one looks simpler, solve that one first, and then use complementary slackness to simplify the other problem, right? So in the problem we did, we first solved the minimization problem. We noticed that the constraint on vitamin P was slack, and we used that to simplify the dual problem. It told us that we could ignore the shadow price of vitamin P. We could assume that was 0, and then we only had to worry about the shadow prices of vitamins Q and R. So it simplified the dual problem from 3 variables down to 2, right? And similarly, if you ever find that if you get an optimal solution where one variable is 0, then in the dual problem, the corresponding constraint is going to be irrelevant, right? Because that'll be satisfied. That'll be satisfied with a margin to spare, and it means we can kind of ignore that extra constraint, right? So it's a quite useful technique for simplifying the dual problem, right? And it's also a way of checking your solutions. If you solve both of them, check to make sure complementary slackness is satisfied. It should always be satisfied.